Today is the 25th. I don't know how this is what's happening to our time here, but this is nuts. It's March 25th. It's going to be April soon. Mm-hmm. Yeah, I mean, I like summer as much as the next guy, but I got a lot to do in these last 35 school days. So you're coming along for the ride. Uh, we still got a couple big things we got to get through. So we're going to talk about complex numbers. And boy, it's tough to just say what a complex number is, but primarily the focus is, you guys remember when we talked about square roots of negative numbers, right? Like if we had like the square root of -4, we had a name for that, right? What was that called? Yeah, well, it's 2i, right? Because the square root of 4 is 2, and then the square root of -1 is I. So that's an example of generally what we refer to as a complex number. The thing that we don't tell you, that I don't tell you until today, is that complex numbers can also have real parts to them as well. So this is a type of complex number. This has a name. This is called a pure imaginary number. And in a very confusing note, what's the square root of 9? 3. This is also a complex number. This just happens to be a type of complex number called a real number. So what we're primarily going to focus on in this class are complex numbers that are, by the way, again, both of the things in the white boxes are complex numbers. The types of complex numbers, though, that we're going to focus on are the types of complex numbers that have both parts. They have a real part and they also have an imaginary part. And so an example of a complex number like what we're going to work with for the next few days would be like this: 3 plus 4i. That is a complex number. It's built by two different portions in this particular case. We would look at this 3 and say that's the real part. And then we would look at the 4i and say that's the imaginary part. When packaged together into this statement, 3 plus 4i, they are a complex number. Got it? So we're going to be working with a bunch of complex numbers that look like that. Almost all of our complex numbers for the next few days are going to consist of reals and imaginary, both portions. So I'm going to try to teach you. Oh, by the way, that I should say this just so I can say I did, and someone someday won't say, I can't believe he didn't tell you that. This is a complex number, a plus bi. So if you see it pop up anywhere and someone says, you've never seen that before, that's just the general form of a complex number. It's no different than if I was going to teach you about like quadratic equations, and I showed you all sorts of examples of quadratic equations, and then I put the confusing one on the board and said, oh, by the way, there's a quadratic, right? So the a plus bi is just a generalized form of saying complex number format. A is the real part, b is the imaginary coefficient. Like, done. So I have 3 missions for the day. 2 of them are very closely related. I want to teach you how to add complex numbers, which is the easiest thing, literally probably going to be the easiest thing you've done all year in this class. Subtracting, which should also be about the easiest thing if you follow directions well. And then there's multiplying, which is a little bit tougher. When it gets difficult will be in a couple of days when we do dividing complex numbers. That's a thing. That's a test. But for now, we're going to go through the easy parts. So we should be able to knock all these out in one day. So first off, to be able to add 2 complex numbers, we'll just make one up. Like, let's say we had 4 plus 5i. And notice that I'm putting it in parentheses. The only significance of that is to show you that that complex number, like as a package, is going to be added to this complex number. These are not multiplicative parentheses. It's a very common error that I see is in about 10 minutes when I show you how to start multiplying, sometimes people see parentheses and say, oh, we got to multiply those together and do the whole FOIL thing. And it's like, no. This is just basic algebra. To combine 2 complex numbers like this, all you have to do is take the real part of one and add it to the real part of the other, just like terms. What's 4 plus 2? It is 6 all day long. And then you're going to take the imaginary portions. And because that's a plus sign, our lives are a little bit easier in this case because the parentheses, I don't have to distribute any negatives or change any signs. It's kind of what you see is what you get. So what is 5 i's minus 8 i's? And that, my friends, is how you add a pair of complex numbers. It's like almost like pre-algebra sort of concept when you're adding and subtracting complex numbers. It is literally combining like terms. So when it becomes a little bit more difficult, and I can do my due diligence to show this to young people, but then there's always going to be the rebels who think that my advice is not welcome. So here it goes. If you have a complex number minus a complex number, you would be wise to show one extra step of work. I don't think we needed any work on that last one because that was like pretty easy, right? But let's do 6 minus 4i minus negative 3 minus 10i. And you're not going to win any cool points with me like, wow, that kid's really impressive if you do this in your head. I'm going to show you what I think is the safest and best way to do these subtraction problems. And if you want to go faster, again, I won't like give you any awards for your mental prowess. All right. Whenever there's a minus sign in front of parentheses, you know this by now. You should give it respect. You should know that a minus in front of negative is a very dangerous thing. It means that we have to distribute a negative essentially. So what I always do with a problem like this is I take off the first set of parentheses free of charge because there's like a positive sign in front, right? And like that doesn't mean anything. So I can just take those off and free them. And again, here it is, my advice, take it or leave it. You'll find you never miss these if you take this advice, but you run a dangerous road if you don't. So let's go in and distribute the minus sign. Think of it as a negative. And when you distribute a negative, all it does is just change the signs of things. And so this minus sign is going to fly in and hit that. What's he going to become? Right. And no one ever misses that one. It's this second one. And oh man, is it hard for me, the guy with the red pen, to deal with. So don't mess this up. You can do this. If you take that negative or minus, whatever you call it, and hit it there, what does that become? It does. And so when I see it with my own eyes, I see now that the past is in the past. I don't see that as a negative 3. I don't see it as a negative 10. I see what's down here. And now I can combine my like terms. You would agree, a very simple concept. Do people miss it? All the time. Mind blowing. So we're going to combine our like terms. We're going to put the 6 with the 3. And what are we going to get? 9. And then we have negative 4 plus 10, which is plus 6. And that's your complex number. I could understand if you maybe partially just fell asleep through that part, because that is, I agree, some pretty rudimentary basic algebra. So that's how you add and subtract complex numbers. My advice is, and will continue to be, with addition, don't show work, just combine like terms. With subtraction, take 13 seconds, show that extra step. It'll pay dividends. You'll never miss these. Unless you can't add and subtract, then you get what you get. But assuming that you show the negative distribution, you're going to be just fine. So what I really wanted to talk to you about today, the other portion of your assignment, is going to be multiplying complex numbers. It's way more interesting than adding and subtracting. So let's do 3 plus 2i times 5 minus 7i. So you'll recall from back in the day when probably back in Algebra 1, when we had a math problem like this, like x plus 5 times x minus 3. How many steps does it take to do that red math problem? It takes 4 steps, right? We want to give this full respect. And we're going to go, okay, I know that everyone has to multiply by everyone. So we're first going to do x times x and get x squared, right? And then we're going to go all the way to the outside and we're going to get minus 3x. And then we're going to do the ones that are closest to each other and get 5x, so plus 5x. And then finally, you can do the ones at the back. 5 times negative 3 is negative 15, right? Like you learned this years ago. So when you put your terms together in the middle, you'd wind up with x squared plus 2x. Good, good, good with that? Now, let's apply that thinking to our complex number multiplication, this problem on the board. So here we go. And I'll color code it again for your educational convenience. Let's start with red. What is 3 times 5? All day long, 15. Now I'm going to switch to purple. What is 3 times negative 7i? It is. And I is not a variable, right? Do you guys remember who I is? What is I? It's a number. I'm wondering if I have time to pour some coffee while I wait for this answer. What is I? I'm really glad that we're having this discussion. I is the square root of negative 1. Apparently, it's been a while. That's the imaginary unit. He's like the foundational, fundamental building block of that entire half of the number system that we call the imaginaries. I is the square root of negative 1. That's going to be critical for us to know that. So I is not a variable, but we treat him sort of like one at certain parts in this problem. Like when I do 3 times negative 7i, it's just like as if I were an x, negative 21i. Just it is what it is. And you'll find the same sort of thinking when we do this green problem right here. What's 2i times 5? Plus 10i. It's this part that I think is interesting. When I do the yellow math problem, and we want to, for the first couple of examples, we want to just write it out. And if you just think of I as a variable right now, if I were an X or a Y or a P or an M, what would you say the answer to the yellow problem is? It's perfect. Negative 14 I squared. But it's at this point that we need to now go back over to the right side of the TV and have a discussion about, well, if I is negative 1, what is I squared? I is the square root of negative 1. So I squared is negative 1. Think about it. That's why it's imaginary. You're like, wait, I just squared something and got negative 1. That's because it's the imaginary unit. When you square a square root, the square root just lifts off and you get what's inside. So this piece, I'm going to put a big fat white box around it. This is absolutely critical for you for the next week. I mean, and beyond, but specifically for this week. I squared equals negative 1. Now that's important because I see right here an I squared. What does that equal? Negative 1. So if I take my magic eraser and I get rid of I squared and I put times negative 1, then it would just be plus 14. Correct. So if I rewrite this answer, and I'm going to just switch to all white now, it would be 15 minus 21i plus 10i, plus 14. And what I think is so super dope about that is the fact that something that at first looked imaginary is actually a real number. Negative 14i squared, you're like, oh, you really just equal 14. Cool. And now it's time to combine our like terms. So to build a proper complex number in the form a plus bi, we're going to put our real parts together first. What is 15 plus 14? And then put those i's together. What's negative 21i plus 10i? And that is how you multiply two complex numbers. Follow the 4-step multiplication process. It gets quicker and quicker and quicker the more you practice. Let's go again. Someone write me a complex number. I'm ready. Go. Okay. Can I have another one, please? Yeah, we get to multiply these. I was really hoping you'd stay a little closer to 0, but hey, we're in this together. Let's do this. We're in it to win it. Kinsley has spoken, written our complex numbers. I hope to God someone's got a calculator handy. So here we go. What is 12 times 16? Nice, 192. And I'm heading to the outside now. What is 12 times negative 32i? So minus 384i. And now we're going to go to the middle, these two right here. Whoop, what's negative 8i times 16? Negative 128i. And then it's time to seal the deal. And please do not skip steps. We're not ready for that mental flexing yet. What is -8 times -32? So I'm going to put plus 256, and I'm going to attach my I squared. That's the only time in this process where you ever could get an I squared. It's the only chance they get to multiply together. And now at this point, what does I squared really become? So if I take out the I squared, whoop, and in his stead, I put a times -1, what becomes of this entire back term? It's really just minus 256. What you come to learn today is that I squared really well. It's super cool. There's not a lot of meat on the bone. It's I squared just as a sign changer. If you find an I squared in a term, just change the sign. That's all he does. He's a sign switcher. And at this point, let's combine our like terms. What is 192 minus 256? Uh-oh, got to shut the door. We're vacuuming at 9:10 a.m. Say again. I like that answer. So we have -64, and then we got a whole boatload of I's to put together. Yeah. So this would be logically where you'd maybe say something to yourself like, okay, we can stop the lesson, right? Not quite. So any questions so far on how to multiply or add or subtract complex numbers? Adding and subtracting is just combine like terms. Give a little respect to the minus because it's negative distribution. Multiplying is a lot, but it's not hard. It's like it's not math you can't handle. It's just a process. Don't disrespect it by forgetting that there's 4 pieces to that puzzle. Now we're going to, I'm going to write this one. I wanted to control this problem because I wanted a very particular flavor. And I'm going to ask this, even though I know that sometimes questions that have obvious answers, sometimes people won't answer out of principle because they're like, this is rude. Don't talk down to me. What do you notice about those problems or those complex numbers? Hmm? Right. So they're built by the same A and B essentially, except the B's are opposites from one to the next. There's a name for these, and I do need you to know what this name is. You know, I'm not real big on vocabulary, but if I need you to know something, I'm going to make you write. Well, I'm going to ask that you write it down because whenever I say this, I want you to be able to know what I mean, and I want you to say it back. These are called complex conjugates. And they have a very significant role, and something really neat happens when you multiply 2 complex conjugates together. Let's take a look at what that something is. You might be surprised as to what the answer turns out to be. So let's go through our 4-step process. I'm going to color code to some extent here. So I'm going to start with yellow. What is 5 times 5? Nice. Now I'm going to keep the same color for this next 2 steps because I want you to notice something. And you've seen this before. What is purple times purple? Plus 30i. And I'm going to do the other purple times purple, and I'm going to do it down below. And notice I'm kind of going maybe in a little different order. I don't know. But what do the purple outside ones make? Awesome. And I heard someone say like the I's are going to cancel. Bingo. We've seen this concept before. We haven't seen it with complex numbers with I's, but remember at this point, I in that state is thought of it's not a variable, but we treat it like one, right? And then we realize, hey, those purple things are going to go bye-bye. And now I'm going to head over to green. What is this times this? Very good. So interestingly, when you start with 2 complex conjugates, when you multiply them out, what kind of number are we going to get? Like what's our, we're going to get a real number, which is pretty cool. The yellow number survives, 25. And what does the green number actually become? A plus 36. But then you'll notice that the purple ones, die. And that's why two complex conjugates multiply to make a real number, because the imaginary portions of them just cancel each other out naturally. And then when you add 25 and 36, you get 61. The moral of that story is two complex conjugates will always multiply to make a real answer. Got it? Start doing these quicker in your head. I wouldn't advise off, maybe not at this point, early stage in the game, doing normal complex numbers in your head. Some of you will, but the conjugates you can actually start to do really fast. So let's do another one. Let's do 4 minus 3i. What's his conjugate? Good. And the better you get at this, you'll be able to look right at it and know that the answer is 25, like before you even start. So we're not going to waste our time with the 2 in the middle and the 2 on the outside, because we know their fate is sealed. But what we are going to talk about is this. What is 4 times 4? Okay, now let's quiz you here. What is green times green? It is 9. And this is the part of the lesson where we start thinking, maybe I can go a little bit quicker. Maybe I can see the writing on the wall. And instead of writing minus 9i squared, I just know that it's going to become plus 9. That I squared has the power to take anything and just switch its sign, switch its sign, switch its sign. And the thing is, with conjugates, there will always be a negative in that green answer, because one of them will always be a negative and one of them will always be a positive. Otherwise, they're not conjugates. So the answer to that one is 25. All right, someone give me a complex number. Not Kinsley, because she picks two numbers that are too big. What's his conjugate? What's the answer to 3 plus 5i times 3 minus 5? Well played. Let's go again. How about 7 plus I? And what's his conjugate? What's the answer going to be? It is 50. Let's examine that one a little bit closer, right? What is 7 times 7? 49. And the often overlooked numbers that get us sometimes are the ones. Ones, they cause trouble at any level of mathematics. There's a 1 right here. I'll make it yellow for you. And there's a 1 right there. I'll make that one yellow for you too. And then when we do the yellow multiplication problem, we get negative 1i squared, which is really plus 1, hence the 50. So that is how you multiply conjugates. I don't think you'll see too many of them in today's assignment, but if you happen to see a pair of conjugates, you're like, cha-ching, jackpot, I can do that one super quick. So in today's Delta Math, you'll be asked to add and subtract. And then in the second section, you'll be asked to multiply. And that's it. I want to knock this out in a day so that tomorrow we can start talking about, there's a couple other things. We got to do modulus, graphing complex numbers, and then dividing. And I think that's it for this class. Get her done. It's on Delta Math. The Daddy Delta. All right, I'm all going to give notes tomorrow because it's the ACT. So tomorrow, if you're an ACTer, I'm not going to see you. Tomorrow, if you're not an ACTer, I'll see you in here and we'll work on something else. And we'll get back to it on Wednesday. How's that? You taking that ACT? Yep.